Okay, so let's dive into this paper you sent over.
It's on asymmetric catalysis
Mhm.
and using these metal organic frameworks, or MOFs.
MOS, yeah. And this is a really exciting area, tons of potential.
Definitely fascinating stuff. Now, before we get too far, can you remind me again what exactly asymmetric catalysis is? I always mix it up.
Oh, sure. So
Really
basically,
quick, why is it important?
imagine you want to make a molecule, right? Like a really important drug, maybe.
Okay.
A lot of times these molecules can exist in two forms. They're like mirror images of each other.
Uh-huh.
But often only one of those versions actually works the way we want it to, like in pharmaceuticals.
Makes sense. So how does that...
So asymmetric catalysis is all about controlling the reaction. So we only get that one specific mirror image, not a mixture of both.
Oh, I see. So it's about precision, making sure we create the exact molecule we need.
Exactly. Less waste, fewer side effects. It's a big deal in a lot of fields, not just medicine.
And that's where these MOFs come in, these metal organic frameworks.
Yeah.
Right? They can help us be much more precise.
Yeah, they're like, imagine a building with all these carefully designed compartments. That's kind of what a MOF is like.
So it's like a sponge almost, or like a honeycomb.
Yeah, kind of. But on a much, much smaller scale, we're talking nano-sized compartments here. And each one of those tiny compartments can act as a tiny reaction vessel, almost like a little test tube.
Wow. So we're doing chemistry in these tiny little...
Exactly. And what's really cool is we can actually tune the properties of those compartments,
Okay.
like their size, their shape, even what types of molecules can get in and out, all by tweaking the MOS structure.
So we're basically designing these custom-made reaction vessels to get exactly what we want.
That's the idea, yeah. It's like molecular architecture.
This is really cool. And this paper focused on a specific type of MOF called MIL-101, is that right? What makes this one special?
Yeah, so MIL-101 is interesting. It's got these really large pores, much bigger than a lot of other MOFs. So it's kind of like if other MOFs are like small apartments, this one's got these huge ballrooms.
Okay, so plenty of space to work with.
Yep. Exactly. And that's key because we want to do reactions with bigger, more complicated molecules, and we need the room for that to happen.
Right, right. And heterogeneous asymmetric catalysis, that's the whole point here, right? To make these catalysts, which we can easily remove after the reaction's done.
Exactly. So in traditional catalysis, what we call homogeneous catalysis, the catalyst is all mixed up in the solution with the reactants. And it's a real pain to separate them afterwards. It's like trying to, I don't know, get sand out of your swimsuit after a day at the beach.
Oh, yeah, not fun.
It's a mess. But with heterogeneous catalysis, the catalyst is in a different phase, usually a solid, so it's way easier to remove. Like, think about making tea.
Right.
You use a tea bag, you get all the flavor, but then you just take the bag out, no mess.
And that's kind of what we're doing here with these MOFs. They're acting like our tea bags for these super precise chemical reactions.
Yeah, that's a great way to put it.
So we have these MOFs, our tiny reaction vessels, but then in this paper, they didn't just use any catalyst, right? They went and built one right inside the MOF itself.
Yeah, this is where it gets really cool. So they took a chiral ruthenium complex, which is a common type of catalyst,
Okay.
and they attached it directly to the organic linkers inside the MIL-101 pores.
So they're basically, anchoring the catalyst directly to the walls of those tiny reaction chambers.
Exact.
Clever. But how do they make sure it attaches in the right way?
That's where this glycine-proline linker comes in.
Okay.
It acts like a molecular arm. It holds the ruthenium catalyst in just the right position within the MOF's pores, and without this specific linker, it wouldn't work nearly as well.
Wow, so it's all connected. Every little piece has to be just right.
Precisely. That's the beauty of chemistry.
Well, speaking of which, how did they actually test out this new catalyst? What did they have it do?
They used a reaction called asymmetric transfer hydrogenation.
Asymmetric what now?
Yeah, it's a mouthful. We just call it ATH. Basically, it's a way to add hydrogen to a molecule, but doing it in a way that creates a very specific handedness. Remember chirality, the mirror image thing.
Right, right. So it's using hydrogen to nudge those molecules into the exact shape they need to be in?
Exactly. Very important for making things like pharmaceuticals and other fine chemicals where even subtle differences in structure could be really important.
So we've got our catalyst attached to our MOF, ready to do its thing. What happened when they actually ran the reaction? Did it work?
This is where it gets really interesting. It worked amazingly well, actually.
Oh, yeah. How so?
So get this. The MOF-based catalyst, it showed like 3 times higher enantioselectivity compared to if you just used the same catalyst, but without putting it inside an MOF.
3 times? Whoa, that's a big difference. So it wasn't just like making the reaction kind of work. It actually made it way more precise.
Exactly. It's like the MOF was guiding things, making sure the reaction happened in just the right way to get that specific enantiomer.
It's like the MOF is like like a chaperone at a molecular dance, making sure everything goes smoothly.
Uh-huh. I like that analogy. But yeah, it's really interesting because they also found something else that was kind of unexpected.
Oh.
So you remember how we were talking about chirality, how
Mm.
those molecules can be like left or right-handed?
Yeah, the mirror images.
Right. So when they used the catalyst inside the MOF, it actually produced the opposite enantiomer compared to when they just used the catalyst by itself.
What? So the MOF like flipped the switch? How is that even possible? It's like defying expectations.
It's all about the structure, you see.
Okay.
Those pores in the MOF, they're not just empty space.
Right.
They actually create a very specific environment around the catalyst.
Uh-huh.
So it's like, imagine you're trying to fit a key into a lock.
Okay, I'm with you.
If the lock is just floating around, it's harder to get the key in, right? But if the lock is held in place, it's much easier.
So the MOF is like the door frame holding the lock steady?
Exactly. The MOF's structure helps to hold the reactants in just the right position so that they interact with the catalyst in a very specific way.
Wow, so it's not just about having the right catalyst, it's about controlling the entire environment around it too.
Exactly. It's like the MOF is setting the stage, creating the perfect environment for that reaction to happen with the highest possible precision.
Okay, so how did the researchers actually figure out what was going on at that level of detail? Because we're talking about things happening at the, atomic scale here? How can they even see that?
That's where they use some really powerful computational tools. They use something called density functional theory, or
I
DFT.
see it. Okay, is that like simulating the whole thing on a computer?
Yeah, basically.
So they can like zoom in and see the molecules interacting?
Exactly. It's like having a superpowered microscope that lets them visualize the interactions between individual atoms.
Wow. So what did they find out? Did DFT give them any clues about why the MOF was having such a big impact?
They found that these really subtle interactions, called Chich interactions, were playing a much bigger role than anyone had realized before.
Chosh interactions. Okay, you've definitely lost me now.
Uh-huh. Yeah, it's a bit of a mouthful. But basically, there are these weak attractive forces between certain parts of molecules.
Okay.
And they're usually pretty weak. But in the confined space of the MOF, they get amplified. It's like, think about those Velcro strips.
Yeah.
One little hook and loop by itself is not that strong.
Oh, right.
But get a whole bunch of them together, and suddenly it's really hard to pull apart.
So these Chosh interactions, they're like the molecular equivalent of Velcro. Small but mighty when they all work together.
That's a great way to put it. And the DFT calculations showed that these interactions were happening between the reactants and the MOF linker itself.
So the MOF wasn't just a passive scaffold, it was actively participating in the reaction through these subtle forces.
Exactly. And those weak interactions, they were enough to nudge the reaction in a completely different direction, leading to the formation of that other enantiomer.
Wow. Okay, so that's one very successful reaction. But what about the bigger picture here? Can we apply this to other reactions, other MOFs? What are the implications of all this? So we've seen how this works in one specific case, but what does this all mean in the grand scheme of things?
Well, this is what makes this research so groundbreaking. It's not just about this one reaction or this one MOF.
Right.
It really changes the way we think about MOFs and catalysis.
Okay, how's that?
For a long time, people thought of MOS as kind of like inert scaffolds, just something to hold the catalyst in place.
Yeah, just a platform.
But this study shows that they can actually play a much more active role. They can actually influence the selectivity of the reaction itself.
So it's like the MOF is part of the recipe, not just the mixing bowl.
Yeah, exactly. Like, it's not just about what you put in the MOF.
Yeah.
It's about the MOF itself. Its structure, those subtle interactions we talked about, they all matter.
Right. So it's a whole new level of control that we didn't really have before.
Exactly. And the DFT calculations, that's another really important part of this.
Yeah, remind me how cool that is. They can actually see those tiny interactions happening.
It's like this whole hidden world that we're just now starting to understand.
So we've gone from thinking of MOFs as these simple scaffolds to realizing they're like these complex microreactors.
Exactly. With all these levers and dials, we can adjust to fine-tune the reaction.
Wow, that's amazing. And this is just the beginning, right? There's so much more we can do with this knowledge.
Oh, absolutely. This opens up a whole world of possibilities for designing new catalysts, new materials.
It's like having this incredibly precise toolkit, and we're just starting to figure out how to use it.
Exactly. And the implications for things like drug discovery, material science, even renewable energy, they're huge.
It's really exciting to think about.
Yeah, it makes you wonder what other secrets are hidden within these MOFs, just waiting to be discovered.
Well, on that note, I think I'll have to leave it there for today, but this has been a truly fascinating deep dive into the world of MOFs and asymmetric catalysis.
It really has. Thanks for having me.
And for everyone listening, thank you for joining us. We'll be back next time with another deep dive into the latest scientific breakthroughs, but until then, keep those brains buzzing.